Welcome to this M1 video on friction and static particles. Now, in this case, when a body, like a particle, a box, whatever it may be, is in static equilibrium under the action of a number of forces, like including weight, friction, and so on, you need to consider whether or not the body is on the point of moving. So when it's on the point of moving, it's said to basically be in limiting equilibrium. Okay, so it's on the very point of moving, and that there is where the frictional force will be at its maximum. When it's in equilibrium but not limiting, then its frictional force will be less than or equal to its maximum. So, it's F max will be equal to mu r when it's limiting equilibrium. Okay, and then when it's not limiting, we have that the friction is less than or equals to mu r. This one is the general kind of equation for friction. Okay, so we don't really put the equals, it's less than or equal to in reality, because friction can take a smaller value than its maximum value. We know this from dealing with it previously. But when it's limiting equilibrium, it means it's on the point of moving. And if you're not told which direction it's going to be moving, then friction could act in either direction, and that will give you a range of values for like a force that you're trying to find. Okay, or sometimes by looking at the forces that you've already got and working out the size of the values, you can work out which way the object's about to move, and therefore find the friction that way. So I think what's best to do here is to look at a couple of examples. Now, I'll start off with one that's just on a horizontal, but all the questions we're going to look at today are on inclined planes. So we've got a mass of 10 kilograms rests on a horizontal plane. So let me draw that first of all. So there's my horizontal plane, and I've got a mass of 10 kilograms. So it's going to be 10g going down, and then it's going to have a normal reaction R. Now, the mass may be modelled as a particle, so I could have drawn just a little circle as a particle here, but I'll leave it as a box. The coefficient of friction between the mass and the plane is 0.4, so mu equals 0.4. Find the magnitude of the maximum force P newtons which acts on this mass without causing it to move if the force of P acts horizontally. So if the force of P is going to act horizontally, then I'll pick a direction. So we'll go this direction, and then the opposite direction is going to be the friction. Now it's because we're looking at the maximum force, then this is going to be in limiting equilibrium. Okay, so it's going to be limiting equilibrium. So therefore we can work out so the first step will be to be able to work out the friction. We need the normal reaction. There's only two vertical forces here, so resolving vertically we get R equals 10g. Okay, and then that is all there is to it that way. Now resolving horizontally, okay, now we can deal with this as F equals ma. The acceleration is 0 because it's not moving, so it's just F equals 0, and that would mean that P minus F equals 0. Okay, but it's far easier with these just to simply put the ones that are moving right equal to the ones that are moving left. So that's my force P, and frictional force is mu R, which is 0.4 times 10G. And that is 39.2 newtons. So that therefore is my force P, the maximum force. Now let's have a look at part B. And part B, the force P acts at 50 degrees to the horizontal. So if I imagine a horizontal line there, then P will act like this at 50 degrees. Friction will always act, parallel to the plane that you're on. Okay, now again, this is in limiting equilibrium. And then what we want to do is just resolve these forces. So this is going to be P sine 50. And this one is P cos 50. So this time when we resolve vertically, we get R plus P sine 50 equals the 10G. And we don't know what R is straight away here. And we resolve horizontally and we get that P cos 50 equals F, where F is mu R. So P cos 50 equals mu R. Now I can take this top one here and make it R equals 10G minus P sine 50 and substitute it in down here. And that will eliminate my R's and just leave an equation in terms of P. Okay, so P cos 50 equals 4G minus 0.4 P sine 50. Take to the other side and then factorize out the P. So cos 50 plus 0.4 sine 50 equals 4G. So therefore P is 4G divided by cos 50 plus the 0.4 sine 50. And that gives me that P is 41.3 newtons to 3 significant figures there. Okay, so since we didn't need R, we can eliminate R and just find out P. If we needed the actual value of R, we could, once finding P, substitute back in to find R. Okay, so that is the first example looked at. Okay, but it's the only one that we're going to look at on a horizontal plane today. But it was just to get you into thinking about this limiting equilibrium. Now let's move on to the inclined planes. So this one, I've got a mass of 8 kilograms and it's at 25 degrees. So I'll just draw a little sloped plane, and I'm going to use a box rather than, like a particle, just because I find it a little bit easier. Okay, so find the coefficient of friction between the box and the plane, and then later a horizontal force is applied. So initially in this case, this as it stands is in limiting equilibrium. Okay, so let's resolve the forces that are currently here. And of course this angle here is 25 degrees, don't forget that. So going down the box will be 8 8g sine 25, and then perpendicular will be 8g cos 25. Okay, just remember this angle is 25, so when you're doing it with the angle that you know is cos, and where the alternative one then is always sine. So that's what we've got. And then if I think of this now in kind of purple, then this mass is going to be pulling the box down the slope. So friction must be acting up the slope to keep it in limiting equilibrium. Okay, so let's resolve perpendicular to the slope, and we get that R is equal to 8g cos 25. And that is 71.1 newtons to 3 significant figures. Now let's resolve parallel to the slope. So that means that F is equal to 8g sine 25, and F is mu R. Now R I already know, and I want to find mu, so I'll just write it up here. So mu is 8g sine 25 over R, which is 8g cos 25. And that gives me the 0.466 to 3 significant figures. Now, since I stored R as A earlier, I'll store this as B. And I like to write the little letter in so I know where it is in my calculator at this point. So that is mu, and that is part A done. Now, a horizontal force P is applied to the box. Given that the box remains in equilibrium, find the maximum value of P. So let's just draw a little sketch again. Okay, so I've just put on these two forces onto the diagram and R. Now, it's a horizontal force applied to the box. So it's going to be applied this way. If it was applied this way, it would just slip down the slope straight away, wouldn't it? So, because this is in limiting equilibrium. So it's got to be applied this way. So rather than put it here, I'm going to put it that side. So it's horizontal, so it's going to be there, and it's going to be P. So that way, this one here, because this angle is the same as this angle, it's going to be P cos 25. And then it's going to act down this way, and it'll be P sine 25 down there. Now, because we want to find the maximum value of P, then the friction is going to then act down the slope. So friction is now acting down the slope. Now, we found the coefficient of friction here, but we'll have a new value of R once this P is applied. So we have to work that out again. So now let's resolve perpendicular to the slope. So we have that R is equal to 8g cos 25 plus P sine 25. Now let's resolve parallel to the slope. So going up the slope, we've got P cos 25. And then going down the slope, we've got 8g sine 25 plus F. And then F is the same as mu R. So 8g sine 25 plus mu R. So what I want is to get R equals for this one. So that'll be P cos 25 minus 8G sine 25 all over mu, which is 0.466. So now I've got these two that are both in terms of R, I can therefore say that 8G cos 25 plus P sine 25 is equal to the P cos 25 minus 8G sine 25 over 0.466. So all that's left to do now is to rearrange this for P equals. Okay, I'll leave you guys to be able to work out the rearrangement here, but you know, it's just a process of multiplying by this, getting the p's to one side, everything else to the other side, factorizing out the p's and dividing by that bracket then. And I got p is 93.4 newtons to 3 significant figures there. Let me know in the comments if I've made a little error there, but I think I've done that right. So let's have a look at a few questions now. Before we do, if at this point you are yet to subscribe, please hit that subscribe button. You know, it doesn't really affect you apart from you seeing a bit more of my videos show up on your feed, but it does help me out immensely. If you've enjoyed this video or at least found it useful, hit that like button, and if you are willing and able to help me out financially, hit that join button. Otherwise, as I said, let's get into the questions. So I've got 4 questions for you today, all past paper questions, or you know, slightly amended past paper questions for you. Have a go at them. Pause the video now. Right, let's look at the next 2. Here they are. Pause the video now. Welcome back. Right, let's have a look at the solutions to these 4 questions. Okay, first question. So, first things first, let's draw a diagram. So, here we have a box. We got R on it, so a horizontal force acts at 20 newtons on a block of mass 1.5 kilograms. So horizontal force that acts on this block, so it's probably going to be pointing towards the block, so I'll just put it in the other side like this. Okay, and this angle here is 30 degrees. Find the normal reaction between the block and the plane. Find the magnitude and direction of the frictional force acting on the block. Hence, find the minimum value of the coefficient of friction acting on the block. So let's resolve these forces. So going up the slope here, this is going to be 20 cos 30 because this angle is 30. So going down will be 20 sine 30. And then in purple, dealing with the mass, we got 1.5g sine 30. I'll do it down like here, 1.5g cos 30. So we've got all of these forces on it, and then there will be a frictional force that we'll have to find in a moment. But first, let's do A, find the normal reaction. So for this, we want to resolve perpendicular. So R is going to be equal to 1.5 G cos 30 plus 20 sine 30. And that is 22.7 newtons to 3 significant figures. And I'll store that in my calculator as A. Now, part B is to find the magnitude and direction of the frictional force. So first, we need to look at what's happening here. So this is the force pulling it down, this is the force pulling it up. We need to see which one is larger, so that then we can see which way friction will act. So 1.5 times 9.8 times sine 30 is 7.35, and 20 cos 30 is 17.3. So from that we can clearly see that that is the larger force, so friction is going to act down the slope like so. Okay, now you don't have to work it out like this, you can just put it into the equation and then the sign will take care of itself. Okay, but I find it easier to know what direction it will be going first, you know. So 20 cos 30 is equal to F plus 1.5 G sine 30. Okay, so you can do it like that. You can, you know, assume it's going one way, and then when you work it out, if it's a negative sign, then it's actually going the other way. Okay, so you can do it, you know, without having to guess, well, having a guess, but not, you know, actually working these values out and knowing which direction it's going. Anyway, F equals 20 cos 30 minus 1.5 times G, which is 9.8, times sine 30, which gives me that F is 9.97 newtons to 3 significant figures. Now I stored this as A, so I'm going to store this as B. Okay, and now we move on to part C. Hence, find the minimum value of the coefficient of friction between the block and the plane. So F equals mu R, and that's for the minimum frictional force. So this will be 9.97 equals mu times 22.7. So mu is 0.439 to 3 significant figures. Okay, so that's the minimum value of mu, the coefficient of friction, to stop the block sliding down the slope. Okay, and that is question 1 complete. Okay, question 2, we've got a box of mass 3 kilograms, lies on a rough, not horizontal, rough inclined plane at 40 degrees. So let's sketch that. Okay, so we've got a box R there, and it's 3 kilograms, so 3G going down, and this is 40 degrees. The box is held in equilibrium by means of a horizontal force of magnitude X. So that's going to be pointing into the slope. So I will put it this side of the slope and call it X there. The coefficient of friction between the box and the plane is 0.3, and the box is in limited equilibrium, about to move up the slope. So if it's about to move up the slope, then F, the friction, will be acting down the slope. Okay, so I know this so far. We need to find out what X is. So let's resolve X first of all. So going up the slope, we've got X cos 40. And going down here, we have X sine 40. And then for the 3G mass, we have 3G cos 40. And then down the slope, we've got 3G sine 40. So now I've got all my forces in play. I can go ahead and work out what X is. So let's resolve perpendicular to the slope, and that would mean that R is equal to 3G cos 40 plus X sine 40. Now we've got R and X in this equation, so that doesn't currently help us. So we need to also resolve parallel. And that will be going down the slope will be 3G sine 40 plus the friction, which is mu R. And going up the slope will be X cos 40. Okay, so we need to find X. So from these two equations, I need to make equation 2 R equals and then substitute it into equation 1. So from 2, we get that R equals X cos 40 minus 3G sine 40 divided by mu, which is 0.3. Therefore, 3G cos 40 plus X sine 40 is equal to this here. So now I just need to rearrange to find X. So multiplying up by the 0.3 first of all, you know, we've got 0.3 times 3G cos 40 plus 0.3x sine 40 equals X cos 40 minus 3G sine 40. Now get the x's onto one side and factorize out the x. We got x is cos 40 minus 0.3 sine 40. And on the right hand side we've got 0.3 times 3, which is 0.9. So 0.9 g cos 40 plus 3g sine 40. From this one going this way and this one going this way, and then factorize it. Therefore x equals, and that means that x is 44.8 newtons to 3 significant figures, and I will store that in my calculator as A. Now we need to go ahead, so that's part A done. Now we need to go ahead and work out R. So for that we're going to go, from equation 1. So R is equal to 3g cos 40 plus x sine 40. So times this by sine 40 plus 3 times 9.8 times cos 40, and R therefore is 51.3 newtons to 3 significant figures. And that therefore is question 2 complete. I hope you managed to get those values out. If you did do it in a slightly different way, just let me know in the comments down below. I'm always interested to hear different methods. So we've got another box in this question, and it is placed on an incline slope of 40 degrees. So I'll just sketch that quickly. So that's 40 degrees. I've got my box and the normal reaction there. 0.5 G going down. The coefficient between the box and the plane is 1/5. The box is kept in equilibrium by a light string, which makes an angle of 20 degrees to the plane. Okay, so that means that with the weight pushing down, the string must be acting up the slope here. Okay, so it's a light string. This is 20 degrees. And the tension in the string is T. And we need to find a range of possible values for T. So that means that basically friction could be acting in more than one direction in this case. Okay, because when this weight here, the force acting down the slope, is greater than the force acting up the slope, friction will act up the slope. But when the tension in the string is greater than the force acting down the slope, then the friction will act down the slope. So we're going to have kind of two scenarios going on. But for now, let's resolve these forces. So 0.5 G cos 40, 0.5 G sine 40, and then for T we've got T cos 20 and T sine 20. And then we'll have friction, but it'll be acting in kind of two directions. Okay, so we will deal with this so far because we can find out what R is, because when we resolve perpendicular, sorry, it should be like that. When we resolve perpendicular, friction's not going to be in that because it's going to be parallel to the slope. So R plus T sine 20 equals 0.5 G cos 40. Okay, so we've got a value for R there. And then when we resolve parallel to the slope, we've got two options. Okay, so option 1 is with the friction going down the slope, and option 2 is with the friction going up the slope. So we've got T minimum times cos 20 plus friction is equal to 0.5 G sine 40, or we have T maximum cos 20 is equal to 0.5 G sine 40 plus friction. Okay, so there's two kind of options there. Now the friction is mu R, so I'll just replace it by mu R, and actually mu is 1/5, so 0.2 R, 0.2 R in both these cases, and R up here is 0.5 G cos 40 minus T sine 20. Okay, so I can substitute in for R into both of these equations. So I'll call this equation 1, equation 2, equation 3. So first of all, we're going to sub 1 into 2. So we have T minimum cos 20 plus 0.2 times 0.5g cos 40 minus T minimum sine 20 equals 0.5g sine. Squeeze that in there. So now I need to basically rearrange this for T minimum. So T minimum, so that'll be cos 20 minus 0.2 sine 20, and that's going to be equal to 0.5g sine 40 minus, now 0.2 times 0.5 is 0.1, so it'll be 0.1g cos 40. Sorry, just moving around there to fit it in. So T minimum equals, so T minimum is 2.75 newtons to 3 significant figures there. Now I need to do exactly the same, so but with equation 3. So substitute 1 into equation 3. So this time we have T max cos 20 equals 0.5g sine 40 plus 0.2 times my 0.5g cos 40 minus T sine 20. So 0.5g cos 40 minus, struggle to fit this in, let me move this across, T max sine 20. Okay, and then all that's left to do is to rearrange like before to find out my T max value. And that gives me a value of 3.87 newtons to 3 significant figures. So the range is, well, I can maybe put it here, and 3.87 and 2.75, or put it in words there for the range of possible values. Okay, but it's just between the T minimum and T maximum. So I hope this one made sense and you did follow what I was doing. Okay, I might have actually, in the real exam where I might have had a bit more space, I might have drawn one diagram with for the T minimum and solved that, and then just put a separate diagram with the T maximum with the friction going the other way and solved that. Okay, but this is perfectly acceptable. Anyway, let's get into the last question. So last question, we've got a box of mass 2 kilograms. So that's 2g. There is the normal reaction. This angle is theta, where tan theta equals 3/4. So that means opposite over adjacent. So this one is 5. So sine theta is 3/5 and cos theta is 4/5. Okay, so that will help us. A horizontal force P newtons acting into the plane is applied to the box. So this direction here is P. Given that the box remains in equilibrium, find the maximum possible value of P. So it's in limiting equilibrium as it stands. So that will be before P acts on it. So let's start off with, before P acting on this box. And we've got, this will be 2g sine theta and 2g cos theta. And so friction will be acting up the slope, like so. So I want to resolve perpendicular. So R equals 2g cos theta. Cos theta is 4/5, so 2g times 4/5. So 8/5 g. I'll leave it like that for now, newtons. Now, we don't know mu, do we? Okay. So let's resolve up the slope parallel. We've got friction equals 2g sine theta. So mu r equals 2g times 3/5. So mu is equal to 3/4. So now that we've got mu, we can now put in our value of P, sorry. So we've got this. I won't worry about some of the forces now, but I'll put the 2g sine theta on. Going up the slope, or going horizontal with the slope, we've got P. So that will be P cos theta and P sine theta. Oh yeah, I'm probably going to have to put the other values on here, aren't I? So let's stick my R back on here, and then let's stick the (2g cos theta) back on there. So for it to have the maximum value of P, then friction will act down the slope. So that is basically what's going on now. And now we have to resolve perpendicular and parallel to the slope, because R will have changed now, because R will be equal to 2g cos theta plus P sine theta, won't it? And then if we resolve up the slope, we have P cos theta is equal to 2g sine theta plus mu r, okay, for the friction. Where now we can substitute this r in to here, and we get P cos theta equals 2g, or let's change the cos theta and the sine theta. So cos theta is 4/5, so 4/5 P equals 2g times sine theta, so that's 6/5 g plus mu, and then this is now 2g cos theta. Cos theta is 4/5, so that's 8/5 g plus P sine theta, so 3/5 P there. Okay, and mu is 3/4, so I'll rub that out and pop a 3/4 in there. So now I can rearrange to find out what P is. So we've got 3/4 of 3/5 is 9/20, and 4/5 minus 9/20 is 7/20. So 7/20 of P. And then we've got 3/4 of 8/5 G, which is 6/5 plus 6/5. So we've got 12/5 G there. So 12/5 times 9.8 divided by 7/20 gives me that P is 67.2 newtons. So hopefully you managed to follow me there. I was going, I wouldn't say quickly, but I wasn't really hanging around. I didn't have a lot of room left on my screen to kind of sort everything out in multiple steps. So hopefully you're able to follow me there, and hopefully you've got some use out of this video. Now this is the last video on statics of a particle. The next video we move on to moments and the last bit in M1. So see you there.